How gravity might have appeared to Newton was enough to allow us to journey from anywhere on Earth to the moon at any given time. Lose yourself in the pulsating beat of time, reflecting on whether our understanding of it is just the peak of the enormous iceberg that lies on its surface. Revelation is more than just a theory. It could unlock pathways to the universe's mysteries, shedding light on a much larger universe, more complex and inspiring than ever before. Imagine how Brian Cox's most recent theory challenges our conventional understanding of time and what it could mean for how we see the real world. Join us on an engaging exploration through the annals of time itself as we delve into Brian Cox's groundbreaking new hypothesis on the nature of time across the vast cosmos around us. Secrets await discovery, and some of these secrets revolve around perplexing concepts of time and gravity, essential components of our existence. Imagine a world in which time behaves strangely. It can slow down or speed up, and the force that keeps us anchored to the ground may not be what it seems. This is the realm of Albert Einstein's theory of relativity, in which our understanding of gravity and time takes an unexpected turn. Albert Einstein, a famous figure, gave us a novel way to view the universe through his theory of relativity. His work established the basis for understanding how time functions in various contexts, especially when moving extremely quickly. This journey began in the early 1900s when Einstein proposed two revolutionary theories: special relativity and general relativity. The special theory of relativity, published in 1905, transformed our perception of reality. Simply put, it informs us that the laws of physics are the same for all observers who are not accelerating. This theory introduced relativistic phenomena, including the fascinating idea that time can stretch or shrink depending on specific circumstances. One famous thought experiment used to illustrate time dilation is the light clock. Imagine being inside a spaceship traveling near the speed of light. Inside the spaceship, a light beam bounces between two mirrors facing opposite directions. According to physics, the speed of light is constant for all observers, so the light beam must appear to travel along a longer, angled path. For both an observer inside the spaceship and one outside, the time it takes for the light to complete its journey should be the same. However, because the light must traverse a longer distance for the outside observer, it seems to take longer. This time difference is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary one. The concept of relativistic effects is more than just theoretical. Scientists use massive machines like particle accelerators, such as the Large Hadron Collider, to accelerate particles to incredibly high speeds. When objects travel at such velocities, we must measure time in a unique way to make precise calculations and predictions. Einstein's 1905 formulation of special relativity changed how we comprehend the cosmos, particularly regarding motion and time. This theory contradicts our everyday experiences. Normally, we assume that increasing a moving object's speed simply makes it go faster. However, according to Einstein, nothing can exceed the speed of light. This is the ultimate speed limit. From this viewpoint, events that seem simultaneous to one observer may not appear the same to another observer traveling at high speeds. Another concept stemming from relativity is length contraction, which means that an object in motion appears shorter along the direction of its motion when observed from a stationary point. Additionally, Einstein's famous equation, E=mc², reveals how energy and mass can transform into one another. This principle is crucial for understanding the behavior of tiny particles moving rapidly and for processes like nuclear fission. Special relativity isn't just an abstract theory, it has practical applications, such as in GPS technology. When GPS satellites transmit signals to your device, their movement causes time to behave slightly differently for them compared to observers on Earth. If we didn't account for time dilation in GPS calculations, navigation systems would be inaccurate. Special relativity teaches us that time isn't constant, it depends on motion. This idea challenges our fundamental comprehension of reality. It suggests that the ordinary laws we use to explain the universe may be incomplete. According to special relativity, time isn't fixed, it's influenced by motion. Key concepts, such as the constancy of the speed of light and the relationship between energy and mass, have been confirmed through various experiments. But Einstein didn't stop there. In 1915, he proposed the general theory of relativity, which explores the deep connection between gravity and the structure of the universe. This theory overturned the old notion that gravity is simply a force pulling objects from a distance. Instead, it explains that gravity results from the bending or warping of spacetime by massive objects. Imagine spacetime as a large, stretchy fabric. When a massive object like the Earth is placed on it, it creates a depression. If you place a smaller object, like a ball, near this depression, it will roll toward it. This is how objects respond to gravity, not due to a mysterious force but because of the bending of spacetime. General relativity provides a thorough explanation of how objects move within our solar system. For example, it accurately predicts how planets orbit the Sun. The Earth's elliptical orbit can be precisely calculated using this theory. Brian Cox points out that this is a stark contrast to older ideas of gravity, which struggle to explain planetary movements. One of the first major confirmations of general relativity came in 1919 when Sir Arthur Eddington led an expedition during a solar eclipse. He observed that light from distant stars bent as it passed near the Sun, just as Einstein had predicted. This provided significant evidence supporting the theory. General relativity also demonstrates that gravity affects time. In areas with intense gravitational fields, time moves more slowly compared to regions with weaker gravity. For example, if you were near a massive object like a black hole, your clock would run slower than one far away from its immense mass. Black holes, one of the most extreme consequences of general relativity, are regions where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole, known as the event horizon, marks the point of no return. Once something crosses this boundary, it is inevitably pulled into the black hole. The concept of black holes has fascinated scientists for decades. They are not just theoretical constructs, we have observed their effects on surrounding stars and gas clouds. When matter falls into a black hole, it forms an accretion disk, a swirling, superheated ring of gas and dust. As this material spirals in, it emits powerful radiation, which we can detect using telescopes. One of the most groundbreaking confirmations of black holes came in 2019 when the Event Horizon Telescope captured the first-ever image of a black hole. This historic achievement provided visual evidence of the existence of these mysterious objects, reinforcing Einstein's predictions from over a century ago. But black holes are not just fascinating cosmic anomalies, they also play a crucial role in our understanding of time. Near a black hole, time slows dramatically due to its immense gravitational pull. This phenomenon, known as gravitational time dilation, means that an observer close to the event horizon would experience time much more slowly compared to someone far away. If an astronaut were to approach a black hole, they might perceive only minutes passing, while years could go by for an observer at a safe distance. This concept was famously depicted in Christopher Nolan's film Interstellar, where astronauts visiting a planet near a supermassive black hole experienced extreme time dilation. The science behind this portrayal is accurate. Gravity has a profound effect on the passage of time. Brian Cox, along with many modern physicists, explores these ideas further, questioning whether time itself might be an emergent property rather than a fundamental aspect of reality. Some theories suggest that time may arise from deeper physical laws that we have yet to fully understand. If true, this could revolutionize our understanding of the universe and our place within it. One of the most intriguing implications of Einstein's theories is the possibility of wormholes, hypothetical tunnels through spacetime that could connect distant parts of the universe. If wormholes exist, they could provide shortcuts across vast cosmic distances or even allow for time travel. While purely speculative at this point, researchers continue to investigate whether such phenomena could be possible within the framework of general relativity. Additionally, modern physics is now exploring the connection between relativity and quantum mechanics, the branch of physics that governs the behavior of particles on the smallest scales. Einstein's theories work exceptionally well for explaining large-scale cosmic structures, while quantum mechanics explains the behavior of atoms and subatomic particles. However, these two theories are fundamentally different, and reconciling them into a unified theory, often called quantum gravity, remains one of the biggest challenges in physics. Some cutting-edge ideas, like string theory and loop quantum gravity, attempt to bridge the gap between relativity and quantum mechanics. These theories propose that spacetime itself may be composed of discrete, fundamental units, rather than being a smooth and continuous fabric. If true, this could lead to a deeper understanding of black holes, gravity, and even the origins of the universe. Ultimately, the study of time and gravity is far from complete. As we continue to explore the cosmos, new discoveries may challenge our current understanding and lead to even more profound insights. From Newton's early observations to Einstein's revolutionary theories and beyond, the quest to understand time and gravity remains one of the most exciting scientific journeys of all time. The universe holds countless mysteries, and with each new discovery, we come closer to unlocking its secrets. What lies ahead may forever change the way we perceive reality itself. Einstein's major aspects of the general theory of relativity and its implications for the structure of the universe began with his introduction of a cosmological constant in his equations. He initially believed the universe was static. However, when scientists discovered that the universe was expanding, he later referred to this as his excellent mistake. The concept of an expanding universe, based on general relativity, constitutes the core of the Big Bang theory, which explains the origin of the universe. Another important idea from general relativity is gravitational waves. These are ripples in spacetime created by the motion of extremely massive objects, such as when black holes or neutron stars merge. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time, offering more evidence in support of Einstein's theory. Over time, scientists have conducted numerous experiments to test general relativity, and it has always stood up to scrutiny, whether through studying planetary motion, observing the bending of light, or detecting gravitational waves. While some may be astounded by the everyday reality of gravity, in the world of physics, it is natural to challenge and question established hypotheses. The case of gravity has sparked a flurry of research into how we think about this essential force. One theory that challenges traditional gravity is called modified Newtonian dynamics, MOND, which suggests that gravity behaves differently, particularly at low speeds within galaxies, without requiring the existence of dark matter. Unlike theories that add unseen matter, MOND proposes that gravity strengthens at low speeds. The gravity debate also involves the elusive ideas of dark matter and dark energy, which were introduced to explain certain cosmic phenomena. Critics argue that these ideas may not be necessary and that alternative theories could explain what we observe. Some scientists who reject Einstein's theory of gravity explore other potential explanations, such as unknown particles or forces that might adjust or improve our understanding of gravity. It is important to note that in science, new ideas are rigorously tested to see if they hold up. For example, Einstein's idea of time as the fourth dimension, where time travel could be restricted by the speed of light, has been paired with creative concepts like wormholes, which could act as shortcuts in spacetime. Stephen Hawking's chronology protection conjecture suggests that traveling back in time is improbable from a physics standpoint. Ongoing experiments and observations aim to determine whether these new theories can account for phenomena such as gravity in a way that aligns with established scientific expertise. Despite the variety of theories explored, none have successfully replaced general relativity, which remains the most well-supported theory of gravity. Testing established ideas is fundamental to the progress of science, and these investigations provide comprehensive insights into the universe. As for gravity, general relativity is still the most important and well-tested theory to date, explaining various phenomena like planetary motion and the bending of light around massive objects. Its capacity for explanation and simplicity continue to validate it. Numerous observations, such as the way planets orbit the Sun, further support Einstein's special and general theories of relativity. Einstein's special theory of relativity reveals that time behaves differently depending on one's motion. This has practical implications, particularly in space travel. Space exploration is thrilling but immensely challenging due to the vastness of space. Additionally, in accordance with Einstein's theory, the speed of light is the maximum speed at which anything can travel. This creates an enormous obstacle for space travel, especially when trying to reach the nearest stars due to their immense distances. To better grasp how time behaves during space travel, we can consider the well-known twin paradox. In this thought experiment, one twin stays on Earth while the other embarks on a swift journey to a distant star. When the traveling twin returns, they discover that they have aged significantly less than their sibling who remained on Earth. This signifies that they have effectively traveled forward in time. Time plays a critical role in space travel. For those who travel at high speeds, their clocks slow down. If astronauts were to travel to nearby stars, time dilation would become significantly more noticeable. They could age more slowly than those remaining on Earth. Although it may seem like science fiction, this is a real effect predicted by relativity. Imagine a mission to a distant star system. Given the vast distances involved, such a journey would take many years, even at high speeds. Astronauts on board the spacecraft would experience time at a slower rate compared to those on Earth. Time dilation affects both living beings and technology. For example, GPS satellites must account for time dilation to function accurately, as they experience time differently than people on Earth's surface. If these differences were not accounted for, positioning errors would occur. Finally, let us examine why time seems to move in only one direction. Time governs our existence, always progressing from the past to the present and into the future. But why does time flow this way? This question relates to the concept of entropy, which measures how disorder or randomness increases over time. Entropy, linked to the arrow of time, tends to grow, causing time to progress in one direction. The second law of thermodynamics asserts that in any closed system, total entropy will either increase or remain the same. In simpler terms, entropy naturally increases and never spontaneously decreases. This growing disorder helps us understand why time appears to have a one-way flow, as seen in everyday events like ice melting or a stirred cup of coffee becoming chaotic. The nature of time and its implications. The idea that time flows in one direction is deeply connected to both thermodynamics and cosmology. As entropy increases, it defines the arrow of time, meaning we only experience events in a forward sequence, never backward. This is why we remember the past but not the future, and why causes precede their effects. However, some physicists have explored the possibility that time may not be as rigid as it seems. In quantum mechanics, for example, time does not always behave in the straightforward way we experience in daily life. Some interpretations of quantum physics suggest that particles can exist in multiple states at once and only choose a state when observed. This has led some to speculate whether time could function similarly at a fundamental level. Time travel, science fiction or reality? One of the most intriguing questions about time is whether it is possible to travel through it. While science fiction often depicts time machines and paradoxes, the reality is more complex. Einstein's general relativity allows for theoretical scenarios where time travel might be possible under extreme conditions. For example, wormholes, hypothetical tunnels in space-time, could, in theory, connect different points in time as well as space. If such structures exist and could be stabilized, they might provide a way to traverse time. However, no experimental evidence supports the existence of wormholes, and many physicists believe they would collapse too quickly to be used for travel. Another theoretical possibility involves the concept of a closed time-like curve, a path through spacetime that loops back on itself, allowing an object to return to its own past. While solutions to Einstein's equations suggest such curves could exist under certain conditions, most physicists believe that natural laws, such as the chronology protection conjecture proposed by Stephen Hawking, would prevent their practical use. Relativity and the expanding universe. The discovery that the universe is expanding has profound implications for our understanding of time. If we rewind the clock, we find that the universe must have originated from a single, incredibly dense point, a concept that forms the foundation of the Big Bang theory. This expansion is accelerating due to the mysterious force known as dark energy. Dark energy makes up about 68% of the universe, yet its nature remains one of the biggest mysteries in physics. If the expansion continues indefinitely, it could lead to a scenario called the heat death of the universe, where entropy reaches a maximum, and all energy is evenly spread out, leaving no structure or usable energy for work. This would mark the ultimate end of time as we understand it. Alternatively, some theories propose that the universe might eventually stop expanding and begin contracting in a big crunch, potentially leading to a cyclic universe where time resets and a new cosmos emerges. Time dilation in everyday life. While relativistic time dilation primarily affects objects moving at extremely high speeds, we actually experience small effects of it every day. For instance, astronauts aboard the International Space Station age slightly slower than people on Earth due to their high velocity and weaker gravitational field. The difference is tiny, fractions of a second over months, but it confirms the principles of relativity. Similarly, GPS satellites must constantly adjust their clocks to account for both special and general relativistic effects. If these corrections were not made, GPS systems would quickly become inaccurate, demonstrating that time is not an absolute constant but rather a flexible dimension influenced by motion and gravity. The future of time studies. As scientists continue to study time, gravity, and the structure of the universe, new discoveries may revolutionize our understanding. The development of quantum gravity, a theory that unites quantum mechanics with general relativity, could provide deeper insights into how time functions at the smallest scales. Additionally, advancements in space travel could push the limits of human experience with time dilation. If we develop faster spacecraft capable of reaching a significant fraction of the speed of light, astronauts could travel to distant star systems while experiencing much less aging than those left behind on Earth. The mystery of time remains one of the greatest questions in physics, linking everything from black holes and cosmic expansion to human perception and technological progress. Whether through theoretical physics, space exploration, or quantum experiments, our understanding of time will continue to evolve, shaping the future of science and discovery.